in the statically indeterminate problem where we have a composite post, wood on the inside, and then on two of the four sides of this wood block we've got two steel plates. We discover when we use the linear elastic model, remember we have this cap that we pull off as a free body diagram, and then the total resistance is the sum of the wood and the steel. They have the same displacement as the cap moves down, so the deformation of the wood and the steel are the same. And so that in the elastic analysis here now with the axial force deformation relationship, EA over L is the basic model, etc., 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 all the way on down, we find out that the steel is real close to the yield, and certainly would violate a practical factor safety, but it's okay. It is linear elastic. However, the wood slightly exceeds its yielding stress. So the system is not elastic in its overall performance. And that leaves the question of, well, what do you do? Is it possible that the system can actually resist this at 180 kips or not? And so the way we want to approach this is by recognizing that both materials have a stress-strain relationship that has a ductile type behavior. That after we hit the yield stress and the yield strain, that the material can continue to accept strain, although if it's elastic, perfectly plastic, there's zero slope on the stress-strain curve after we hit the yield strain. And that's what we want to take account of, that the wood yields first, and it's going to march out into the plastic region. And it's going to change a few little things in our analysis. It won't change equilibrium, that in this system the 180 kips is resisted by both the steel and the wood. It doesn't change that the deformations of the wood and the steel are also going to be equal to the cap. But since the wood has yielded, what that means for us is that our stress in the wood is going to be equal to its yield value, which is only 2 KSI. That actually makes life simpler when we look at this relationship here. That means that our sum of NS plus NW now is going to be whatever our stress in the steel is times our area of the steel plus now 2 KSI times, because now that the wood has yielded, that's what we've already figured out, times its area, which is 36 square inches. Right? And so we find out, of course, that's 72. The whole thing has to be equal to 108, and we don't know yet what the steel stress is, but the steel area is 3 square inches. Right? And so now we go and we find out, okay, 108 minus 72, that equals 108 kips. We'll divide by the 3 square inches. That's our stress in the steel, and lo and behold, we're going to find out that that is equal to exactly 36 KSI. And that happens to be equal to the yield stress in the steel. That's just in a sense, a coinkydink, that if when the wood has yielded, the steel now is the only thing that can accept additional load. It tries to take the rest of the load. It increases its stress all the way up to 36 KSI, and that so happens to equal the yield. So it is possible here. What we've actually reached is total system capacity, that the steel has also yielded. And that means that if we were to plot, for instance, the force deformation relationship between the total applied force in the system and our capacity, our delta of the cap, that is, what we would find is that originally our system has both the steel and the wood behaving in a linear elastic fashion. We find then that the wood has yielded, and it will have yielded first. It won't take very long before the entire system reaches its capacity, which is 180 kips. Because what's really happening here is that you've got, at whatever the displacement values are, we don't know what they are, we haven't calculated them yet, but the wood is a relatively flexible system, and it yields at whatever this original total system force is, which is, we'll call P sub y, and then the wood just runs out flat. The steel, on the other hand, yields, because we found out here at 180 the whole thing was gone, then we know that actually this is at some lower value. These aren't supposed to be exactly identical here. That would be your steel behavior. That was your wood, and then the stop one was your system. Everything taken together. Right now, if we went back to our first one, we could take these results, and since everything in the model is linear elastic, what we could do is say, hey, look, we predict a linear elastic behavior that we'd have 2.13 KSI in the wood. That's a little bit too much by some sort of ratio. If we were to take 2 divided by 2.13 times the 180 kips, no, linear elastic behavior, so we can rescale things. If we reduce the load by down to 94% of the 180, we'd have 169 kips when imposed on the system. It's going to bring the wood right up to first yield. It would also mean that the wood, or I'm sorry, the steel would end up at about 32.3 KSI. Right? Everything scales up and down. That is our first yield point. And so that is the 169 kips. The other interesting things here are that we could figure out what our delta y is that goes along with this by, since we know the wood has right at yield at delta y. That means that delta of the wood in that condition would be sigma y, that's n over a times L over E. So that would be 2 KSI. It's 30 inches long. It's got an E of 1800 KSI. And we would find that we'd have a axial deformation of the wood of 0.03 inches. Really, obviously 333 repeating. And since little delta W also equals the system displacement in this problem, that would be about 0.03 inches. It's a little bit more complicated then to go figure out what's happening here at the associated system capacity of that particular displacement. But what you have to do is now let all the additional load go on to the steel to find that other remaining part. What would that look like? Well, let's leave that for another time.